Good morning. We are now discussing few concepts of astrophysics, under which we now study the gravitational potential energy of a star. We derive an expression for the gravitational potential energy of a star. In order to derive the gravitational potential energy of a star, let us now consider a star of mass m, radius capital R, and let this star is formed by the slow gravitational contraction of hydrogen gas spread over millions of kilometers, and these gas particles are assumed to be initially at infinite distance. Let dm, a function of small r, be a small cloud of spherical shell of thickness dr and internal radius r, density rho over a sphere of mass m, function of small r and radius r. Hence, dm is equal to 4 pi r square rho into dr, where dm is the small amount of mass or mass of the cloud that is added to a sphere of mass m, function of r, and that dm is equal to rho into dv, but dv is 4 pi r square dr. Therefore, work done in order to bring this mass and add it to the sphere of mass m, function of r, in the sense mass of sphere of radius smaller. And this work done in order to add this mass is given by the potential energy, that is gravitational potential energy, du equals minus gm dm by smaller. This is the amount of work done in order to add this amount of mass to this sphere. Now, thus total gravitational energy required to form the entire star is given by u equals integral 0 to r minus gm dm by r. We have integrated the previous expression. By integrating this, we can get the total gravitational potential energy required to form the complete star. And here is the innermost circle, which represents capital M, function of small r. The innermost sphere is having a radius small r, and therefore its mass is m, function of r. Otherwise, I can take it as m dash also. And this is the spherical shell whose mass is dm, or the gas cloud, which is added to m. And this is the complete sphere of mass capital M, a function of capital R, that is radius capital R. Now, according to linear density model, we have rho equals rho c into 1 minus r by r. Rho represents the density of the matter inside the star at a distance r from the center. Rho c represents the density at the core or at the center. Now, equation 1 implies dm is equal to therefore 4 pi r square. Instead of rho, we have written it as rho c into 1 minus r by r into dr. This is equation 3. Now, substituting or integrating this, we get the total mass of this innermost sphere. So, integrating this between the limits 0 and r, 4 pi r square rho c into 1 minus r by r into dr. On simplification, 4 pi rho c are constants, therefore 4 pi rho c into integral 0 to r square is multiplied to this, we get r square minus r cube by capital R into dr. Therefore, on integrating, we get m is equal to 4 pi rho c r cube by 3 minus r power 4 by 4r, or m is equal to 4 by 3 pi rho c into r cube. I took r cube by 3 common into 1 minus 3r by 4r. And this, for differentiation, it is a function of r. This is a function of small r. Or we can take this as m dash also in order to differentiate the masses. We can take it as m dash also. Now therefore total mass of the star, total mass of the complete star is obtained when we replace small r by capital R in the above equation, in equation number 4. Therefore equation 4 implies m is equal to 4 by 3 pi rho c into capital R cube into 1 minus 3r by 4r, r gets cancelled, 1 minus 3 by 4 is just 1 by 4. And 4 again gets cancelled, therefore m is equal to pi r cube rho c by 3. This equation 5 gives the total mass of the star. It depends on radius of that particular star and the density at the center. And rewriting this, we get rho c is equal to 3m by pi r cube, the expression for the density at the center or the core density of the star. Now we substitute equation 3 and 4 in 2. So 4 is for m, 3 is for dm, 3 is for dm, and we substitute m and dm from equation 3 and 4 in equation 2. Therefore u becomes minus g, and this is for m and this is for dm whole divided by r, minus g m dm by r. We have substituted for m and dm. Simplifying, we get minus g into 4 pi rho c. We have 4 pi rho c again, that is 4 pi rho c whole square divided by 3 into integral 0 to capital R. This is for the complete star. Into we have r power 5 divided by r, that is r power 4 into 1 minus 3r by 4r into 1 minus r by r into dr. Multiplying this and simplifying, we get u equals minus 16 pi square rho c square g by 3, which are constants, into integral 0 to r power 4 minus 7 r power 5 by 4r plus 3r power 6 by 4r square into dr. Simplified these terms. Therefore it becomes minus 16 pi square rho c square into g by 3 into r power 5 by 5 minus 7 r power 6 by 24r plus 3r power 7 by 28r square, with the limits of integration 0 and r. We have integrated this and so we get this. So substituting the limits of integration in the next slide, you can see u is equal to minus 16 pi square rho c square g by 3 into capital R power 5 by 5 minus 7 r power 5 by 24 plus 3 r power 5 by 28. So taking LCM and simplifying this term, we get u equals minus 16 pi square rho c square g by 3 into 13 r power 5 by 840. That is equal to minus 26 pi square rho c square g r power 5 by 3 into 105, 8 2 za, 8 105 za, 8 105 za. Therefore it is 3 into 2 is 26, 3 into 105 in the denominator, and we are now substituting for rho c square in the next step. So it becomes u equals minus 26 pi square g r power 5 by 3 into 105 into, for rho c square it is 9m square by pi square r power 6. Again simplifying, we get 3 3s are 9, 3 3s are 9, and 3 into 26 is 78. It is therefore minus 78 g m square pi square gets cancelled. Yeah, this r power 5 gets cancelled with this one, left with 1 r. Therefore it is minus 78 gm square by 105 r. It can be rewritten as, this is nearly equal to minus 78 gm square by 104 r, and that will be therefore equal to u equals minus 3 by 4 gm square by r. This is the final expression for the total gravitational potential energy of a star. Thank you.